In this video, we're going to look at using a trigonometric substitution to evaluate the indefinite integral, x cubed over the square root of x squared plus 4. When I look at x squared plus 4, I'm reminded of the following trigonometric identity. Tangent squared of theta plus 1 is secant squared of theta. I'm pairing the x with the tangent of theta, the constant 4 with the constant 1, and I want to turn it into some expression that looks like secant squared of theta. My formula, my expression here has a 4 in it, so I'm going to provide a factor of 4 by multiplying everything through by 4. What's really being squared in this first term is 2 times tangent of theta. So I'm going to think of this as 2 tangent of theta squared, and that suggests to me that I should try taking x to be equal to 2 times tangent of theta. So we're going to do that. We'll take x to be 2 times tangent of theta. What I'm really doing is defining a new variable, theta, and it's related to x according to the arctangent of x over 2. The arctangent function by definition gives you an angle between minus pi over 2 and pi over 2. We can keep track of the relationship between my angle theta, this new variable, and my variable x using a little right triangle to help us keep things organized. What I'm saying in this formula here is that the tangent of my angle is the ratio x over 2. Tangent is the opposite side to the adjacent side. So I'm declaring that my opposite could be x and my adjacent side could be 2. Then the tangent of theta is that ratio x over 2. The hypotenuse, the missing side here, can be obtained by using the Pythagorean theorem and its square root of x squared plus 4. Observe that it's exactly the expression that motivated the trig substitution that we're doing, square root of x squared plus 4 in the integral. The final ingredient that we need is to deal with the derivative, so I'll need to take the derivative of x with respect to theta. X is 2 times tangent of theta, so its derivative is 2 times secant squared of theta. We need to write this as a differential, so I'll separate the variables, bringing d theta over, and we get dx is equal to 2 times secant squared of theta d theta. We're now ready to carry out our substitution. The form of the integral is x cubed over the square root of x squared plus 4. Let's replace our x with 2 times tangent of theta in each instance that it occurs, so I'll have 2 tangent theta here and 2 times tangent of theta here. It's important that you also remember to substitute out the differential dx. In this case, it's 2 secant squared of theta, and so that will appear in our integral as well. Simplifying the expression in the numerator, I have 8 times tangent cubed. I have my factor of 2 secant squared from the differential. And in the denominator, I will have 4 secant squared of theta. Observe that was entirely our motivation. 2 tangent squared of theta plus 4 gets replaced with 4 secant squared of theta. Let's simplify some more. I'll have 8 times 2 will give me 16, and in the numerator I have tangent cubed times secant squared. In the denominator I'll have 2. When I take the square root of a square, like the square root of secant squared though, I get its absolute value in principle. So I'll have 2 times the absolute value of the secant of theta. However, in the quadrant that we're working in, where the angle is between minus pi over 2 and pi over 2, the secant of theta, which is the reciprocal of cosine, will be positive. We're working in quadrants 1 or in quadrants 4, where both the cosine and the secant is a positive number, and I won't need this absolute value. So simplifying here, taking advantage of the fact that the secant is positive for this range of angles, I'll be able to cancel out one factor of secant, and when we're done here we'll have 16 over 2, which is 8, tangent cubed, and the one factor of secant will survive in the numerator. We'll have secant of theta. We now have a trigonometric integral that involves the tangent and secant. You should start to look for derivatives of either tangent, which is secant squared. I don't have that in this expression. So I will look to the derivative of secant, which is secant times tangent, and I'm going to pull that out of the expression over here. I'll have tangent squared times a secant times tangent. That's the derivative of secant. I'll save that for a substitution, and we're going to convert the remaining tangent squared to secant squared using the usual identities. So carrying out the conversion, tangent squared is secant squared of theta minus 1. And we're saving the secant times the tangent of theta for the derivative of secant. We'll let u be secant of theta. Its derivative, its differential, is secant of theta tangent of theta d theta. We'll carry out the substitution. It's 8. Secant squared is u squared minus 1. And then this will all be my du. We integrate term by term. 8, and we'll integrate to get u cubed over 3. We'll integrate minus 8. That 1 will become u. We back substitute to secant, so we'll have secant cubed minus 8 times secant of theta. And now I need to back substitute in terms of x. So I have an expression here that has secant cubed, which will go in this bracket here, and then I have 1 secant of theta that will go in this bracket here. I now look to my triangle to determine what the secant of the angle is. The cosine of theta is adjacent over hypotenuse. The secant is its reciprocal, the hypotenuse over the adjacent side. So I'll take the hypotenuse square root of x squared plus 4 over 2 and replace each instance of secant of theta with that expression. There it will be cubed, and then we'll see it one more time just as a power 1. Finally, simplifying the expression, I'll have 2, which is getting cubed. That will be a factor of 8, which will cancel this one. And I'll have 1/3 the cube of x squared plus 4 with a square root. And then here I have a 2 and an 8. They'll cancel to give me 4, and just the power square root of x squared plus 4 left behind.